Welcome to Machine Learning and its applications. In this first chapter, we introduce machine learning, its core ideas, its main methods, and the kinds of problems it can solve. Machine learning is already part of daily life. When a music app builds a playlist that fits your mood, or a map app predicts your arrival time to the minute, a model is at work. Learning patterns from examples instead of following handwritten rules is the heart of this book. By the end of this chapter, you should be able to explain in plain language what machine learning is, describe how AI, machine learning, and deep learning relate, contrast it with traditional programming, and recognize machine learning in everyday products and across industries. You should also be able to tell apart the three styles of learning: supervised, unsupervised, and reinforcement learning, and outline the stages of a machine learning project, including why data quality shapes the result. Here are the three main paradigms of machine learning. Supervised learning works from labeled examples. Unsupervised learning finds structure in unlabeled data. And reinforcement learning learns by trial and error. Under each one are the representative tasks we will study in this book. So, what is machine learning? It is the practice of building programs that improve at a task by learning patterns from data rather than being given explicit step-by-step instructions for that task. The phrase learning from data is best understood through a problem almost everyone has faced: filtering spam out of an inbox. One way is to write rules by hand. Machine learning turns the problem around. Instead of rules, we give the system a set of messages already labeled as spam or not spam. The model is given no rule. It infers the pattern directly from examples like these. This is the central promise of machine learning, a system that gets better as it sees more data and that can handle problems too messy and too fast changing for fixed rules. Artificial intelligence, machine learning, and deep learning appear together so often that they are easy to confuse. In fact, they describe nested ideas, like circles drawn one inside another. Artificial intelligence is the broadest circle. Machine learning is the part of AI that learns from data rather than following handwritten rules. And deep learning, built on neural networks, is a powerful subset of machine learning. We will spend most of this book on machine learning in general, build up to deep learning in chapters 14 and 15, and then apply it to language, vision, and other domains in the later chapters. The cleanest way to grasp machine learning is to compare it with ordinary programming. In traditional programming, a person writes the rules. In machine learning, we supply the inputs and the desired outputs, and the computer works backward to discover the rules that connect them. Traditional programming is best when the rules are clear and stable, like computing income tax from a tax table. Machine learning is best when the patterns are complex or shifting, like deciding whether a photo contains a cat. The contrast is easiest to see as a picture. In traditional programming, data and handwritten rules go in and outputs come out. Machine learning flips this. Data and outputs go in, and the rules, that is, a model, come out. That flip is the whole idea. Income tax is a perfect job for traditional programming. The rules are written down in law, and they rarely change in the middle of the year. Machine learning is not a new idea, but it has become unavoidable in the last decade for three practical reasons: far more data, much cheaper computing power, and better algorithms. Look at where it already appears: recommending shows and products, scoring credit and catching fraud, flagging tumors in medical scans, estimating arrival times, translating languages, and forecasting demand. Notice that these examples come from business, medicine, engineering, and the public sector alike. Machine learning is not confined to tech companies. Machine learning problems fall into three broad families. Let us look at each one in turn. In supervised learning, every training example comes with the right answer attached called a label. It splits into classification when the answer is a category such as spam or not spam, and regression when the answer is a number such as a price or next month's sales. In unsupervised learning, the data carries no labels. A retailer, for example, might want to group its customers by shopping behavior without deciding the groups in advance. In reinforcement learning, an agent learns by trial and error inside an environment. This is how programs learn to play games at superhuman level, how robots learn to walk, and how systems learn to adjust prices or dispatch vehicles. Beginners often picture machine learning as choose an algorithm and run it. In practice, the algorithm is only a small part of the job. A full project runs through 8 stages. Frame the problem, collect the data, prepare it, choose a model, train it, evaluate it, improve it, and finally deploy and monitor it in the real world. Here is the key point. A machine learning project is mostly a data project. Collecting and preparing data consumes most of the effort, while training is comparatively quick. Strong data beats a clever algorithm trained on weak data. It is tempting to treat a trained model as an oracle, but a model is only as good as the data behind it. Machine learning demands judgment as much as technical skill. To summarize, machine learning learns rules from examples instead of having them coded by hand. And we met its 3 families: supervised learning from labeled answers, unsupervised learning that finds hidden structure, and reinforcement learning by trial and reward. For our first hands-on example, we will train a small model that tells 3 species of penguin apart from a few body measurements. We use the Palmer Penguins dataset, a modern and friendly alternative to the classic iris dataset. Here is the full code. It loads the data, picks 4 measurements as the features and the species as the target, splits the data into training and test sets, trains a decision tree, and prints its accuracy. Even without knowing how a decision tree works, you can read the skeleton every supervised project shares, load the data, separate the features from the target, split into training and test sets, train on the training set, and predict on the unseen test set. The final step is to measure how well the predictions match reality. Run this code and you should see an accuracy well above 90% because the 4 measurements separate the species cleanly. Let us see all of this in one place. A food delivery platform connects customers, thousands of restaurants, and a fleet of couriers. Behind its simple order button sits a stack of machine learning models, each learning from data the platform collects every second. None of these tasks could be solved by handwritten rules. This single app touches nearly every theme of the book: recommendation, classification, and fraud detection, and demand forecasting over time. The following code sketches 2 of those model types: a classification pipeline that assigns an order to a category, and a regression pipeline that estimates a continuous quantity, such as delivery time. The structure mirrors what we saw before. Load the data, split it, fit a model, and score it, once for the classification task and once for the regression task. Running it typically prints a classification accuracy above 95% and a regression error around 0.53, showing that even a minimal end-to-end pipeline can deliver useful predictions for both kinds of tasks. If you want to go deeper, these 3 texts are excellent companions: Mitchell's Classic Machine Learning, the accessible Introduction to Statistical Learning, and the more rigorous Elements of Statistical Learning. That brings us to the end of Chapter 1, our Introduction to Machine Learning. In the next chapter, we turn to the basic concepts that the rest of the book builds on.